Okay, this is what we do. So for this problem, let R be the region enclosed by the graph. Okay, that's the graph. And the horizontal line y equals 4. So first thing I'm going to do is I'm going to label these. This will be f of x. That's this. And the horizontal line y equals 4. That's y equals 4. As shown in the figure. Okay, find the volume of the solid generated when R is rotated about the horizontal line y equals -2. Ooh, that's down here. This is y equals -2. Y equal to -2. And I've rotated about that. Okay, okay. So the way I think of this is with with two integrals. Find the volume of the solid generated when R is rotated about the horizontal line. Okay, so the first integral is going to get the solid that'll look basically like a cylinder, if you can see that. It's just going to be the outside radius. So I'll just take, well, I'm going to do it with one integral. If I can do this, or I mean, I'll do from pi times pi, and then the outer radius would be 4 is the bigger minus the smaller. So that's this distance, that big distance first. That's the big shape. That'll make the cylinder. And that'll be 4 minus -2. So 4 minus -2, all of that will be squared because it'll be pi r squared. And then take away, the inside shape, which will be this shape. And if we rotated that about that axis, we'd get something that looks like that. So we're removing this from the inside. We're removing that volume from the inside. So I can say this distance would be this function, f of x, which is x to the 4th minus 2.3x cubed plus 4. And I'm subtracting because the distance is when I subtract the 2. So subtract -2. And then square that, dx. Now, what I need to find now is the limits of integration. I know that I'm going to go from 0, that's not that bad, 0 till where? I don't know where, so I'm going to put this, I'll set them equal. So I'll put this y, this 4, I'll set it equal over here, and then use my calculator to solve and see where that is. Or, I'll use the intersection function on my calculator. That'll be good. No, wait a minute. I don't even need to use that. I can just set them equal and solve, because the 4's will cancel out. This 4 will cancel out with this 4 to find out my intersection points. I know that 0 is one of them. Whoa, no! I know that 0 is one of them, so I'll go ahead and write that. It's going from 0, that's this part right here, and then let's see, if I say, so this is the intersection. One of them has x equals 0, the other one I can find out by plugging in 4 for my f of x value. And so I have 2.3 x to the 3rd plus 4. I'll subtract 4 from both sides to get 0 equals x to the 4th minus 2.3x cubed. Factor out an x cubed. And that is x minus 2.3. So there it is. X equals 0. That's where you can get the 0 part, and then x equals 2.3 is from there. So 2.3 is what my other limit of integration is going to be, 2.3. And I've rotated it by squaring, by doing the squared part and the pi, because that's pi r squared, and then I'm integrating, so I add up all those disks, and that'll give me part A. Wow. So after I do that integral in the calculator, I get 0.8, well, 0.8, 98.868, 98.868. Let me make sure. Oh no, come on. Okay, so it's 98.868, and It doesn't ask for units, so I don't have to write any units, but they would be cubed, right, because it's volume. You would get 2 points for the integrand, so 2 points for writing this down properly. So you'd have to write that down. You couldn't just do it in your calculator. You have to write this down. You don't have to simplify it. You just have to write that down properly. And then you get 1 point for the correct limits, so you'd have to find the intersection properly. So 1 point for that, and then 1 point for the correct answer. So this one was A was a total of 4 points, and it was a lot. We had to do a lot, so that makes sense. So that's A. All right, A. What does B say? The region is the base of a solid. Okay, so pretend that this region here is the base of a solid, so this will be with a known cross-section. Each cross-section perpendicular to the x-axis, so perpendicular to the x-axis, so we have to integrate with respect to x, is an isosceles right triangle with the leg in R. So if we have an isosceles right triangle, that's going to look like this, where those are congruent. These are 45-degree angles, but in calculus we use radians, so that would be pi over 4. And one of the legs is in the region. So if we have this, looking up, this would be a right angle. It's sticking out, so it's kind of skewed. But we have, that's our cross section. We have to find the area of that and integrate it, again, from 0 to 2.3. So the isosceles right triangle with a leg, find the volume of the solid. Okay, yeah. So we're integrating from, so part B is we're integrating from 0 to 2.3, and it's going to be of some area function dx. So we have to find out that area function, for a triangle, for a right isosceles triangle. So this is going to be inside the region, so I have to find out this distance, and that's simple. We already found out that distance. That's oh no, we didn't find that distance. That would be the bigger minus the smaller. So that'd be 4, right? 4 minus our function. So this is 4 minus what was it? X to the 4th plus or minus? Minus 2.3 x to the 3rd plus 4. Right? Yeah. And then we need to find the area. So that's this distance. It's also that distance. Those are the same because those are congruent. And area would then be 1/2 times the base, which is this, times the height, which is also this. So 1/2 times the 4 minus, well, so this would be area function then, right? 4 minus x to the 4th minus 2.3x cubed plus 4, and that whole thing is going to be times itself. It's going to be squared. And I integrate that, so I'll write down from 0 to 2.3, 1/2 times 4 minus that. The reason why I'm squaring it, again, is because those are the same length. So I'm just multiplying it by itself. Yeah. So there's the integral, and I'll put it in my calculator. And I get out 3.574. That's if I round to 3 decimal places. You can keep more or truncate. And this would be 2 points for getting the proper integrand. So they don't care about the limits because they already graded for that. So it would be 2 points for this and then 1 point for that for a total of 3. That means, what do we have, 7 points? Our last piece, part C, is worth 2 points. Alright, the vertical line x equals k divides R into 2 regions with equal areas. Write but do not solve an equation involving the integral expression whose solution gives the value of k. So we have to write out the equation as if we were to solve it, but we don't have to solve it. So that saves us some time. So there is some line y equals k, right? No, x equals k. Ooh, the vertical line x equals k. Okay. So we have the vertical line x equals k, And somewhere, I don't know what value k is, but somewhere it divides it into two equal areas, right? With equal areas. So what we really do is we integrate for the area of the region. We integrate from 0 to k and then set it equal to k to 2.3. So that's what we're doing. We just need to get the correct integrand. And the integrand, we're just finding the area between two curves. So it's the larger one minus the smaller one. So that's all we're doing. So the integral for part C, and we'll be done with this, is the integral from 0 to k of the top function minus the bottom function. So that's 4 minus whatever f of x is, x to the fourth, minus 2.3 x to the third, plus 4, I think. And that's dx, right? That's the area between those two curves, because I did the top minus the bottom. And then I do the integral from k to 2.3. That has to equal the integral from k to 2.3 of the same thing. So 4 minus x to the fourth minus 2.3 x cubed plus 4 dx. And you'd get 2 points for this problem. One for getting the correct area of the region. So like that would be doing, well, I guess, what would it be? It would be getting the proper integrand and the proper limits, and then knowing to set them equal is another point. And this is it. That's it. We're done with this problem. That took a long time.